Hi, in this video we're going to try to show you how to use Geogebra a little bit more, show you some of the advanced techniques, and give you some 3D ideas of what we've been talking about. So, I want to label my vectors, like let's say A is that vector, I need another point, 1, -2, 3. So there's A going off in that direction. And usually it can be a good idea to make sure we get the tip of that vector right there. And so there's vector A sitting in space. And I make a vector B. So notice how Geogebra gives us a suggestion. It tells us that we can put an object like a point inside, or we can put a starting point and ending point if you want to have a more traditional non-position vector. But for what we're going to do right now, a position vector is just fine. So let's do -2, +1, and 5. Okay, so this guy is pointing out that way, and we'll make sure we give a tip, -2, 1, 5. And what we saw in chapter 12.4 was that these two guys by themselves make a plane. Any two vectors can be found to be in a plane. Now Geogebra makes this easy. We already know the third point we could use is the origin. And I have a handy tool right here, this button, and it says find a plane that goes through 3 points. So I'm going to pick A, and then notice how it highlights the point in a lighter color, C, and B. I don't know if that was B. Okay, good, it was. All right, and so there, yeah, we have a plane going through these 3 points. Now, I know some people were like, I don't understand why we're doing this cross product. Here's why we're doing a cross product. What is Geogebra doing when it finds this plane? When it finds this plane, it's computing the cross product and getting an equation for the plane that would go through these 3 points, which will have a normal vector. So I can do C equals the cross product, and now it says, hey, put 2 vectors in me of A with B. Now, that's some ginormous vector, okay? But it is pointing perfectly perpendicular, perfectly orthogonal to that plane. If you're having trouble seeing it, I'm going to shorten it. Let's say we wanted to do 1/4 times C. We want to scale that vector. And remember what multiplying by a negative would do? Multiplying by a negative would change the orientation, reverse the direction. And that's what the cross product is doing. The cross product is giving me the vector that would be orthogonal to both A and B. And why is that important? Because that helps me to find the plane that we're at. I told you in video for 12.5 that we could have parallel planes. So if I wanted to talk about a parallel plane to this guy, notice it gives me my equation, 13x plus 11y plus 3z, and notice the normal vector, 13, 11, 3. It's a scaled version of these coefficients here. And this is a scaled version of these coefficients. So if I use those same coefficients, 13x plus 11y, it's not on the screen, plus 3z equals 5. Oh my gosh. Oh, typo. Okay, 5 is too close together, but you can already see these are 2 parallel planes. Let's do let's do 10. Okay, fine, let's go crazy. Let's do 100. I'm losing it. 100. Okay, look. So there's 2 parallel planes. Notice how my normal vector is still going to be normal to both of them. I'll make it a little smaller, and maybe we can get what I was looking for. So can we cooperate, GeoGebra? Sure. Sure, GeoGebra. And now we see that this normal vector is normal to both of them because they're both parallel. Now, what happens if I start manipulating this? If I start giving it a negative y, maybe that'll help. If I give it a negative y, we have two planes that are intersecting. And two planes that are intersecting gives us a line. I think there's an option to intersect two objects. Yeah, intersect two surfaces. Bam, bam. And now we have a line going off in that direction. Okay? And that's what we studied in 12.5. It is not an exaggeration to say that you have been studying how to program GeoGebra. I'm going to erase many of these things, and we're going to start looking at what it means for lines to be parallel or skew or intersecting. So there's one line. Now, if I use this exact same direction vector, sorry, it won't tell me the direction vector. I need to make this bigger. Okay, if I use the same direction vector with a different initial starting point, so the commands are a little weird. We're going to do like capital X equals some other point, like 1, 3, 5, plus t times, make sure you do the times, it freaked out at me a minute ago, 0, -2, 86, 86. Now what you have is two parallel lines. These two lines will never intersect, and in fact what makes them parallel is they live in the same plane, right? There's a plane that contains both of them. If I start manipulating things, if I start manipulating this vector, what I'm likely to have happen, let's try to give it a new variable name, y equals 135 plus t times 6, 0, -8. Okay, so now we have two lines that are intersecting at that point they share, and yet these two lines in black will never intersect with the line in blue because they're skew. That's what this looks like. And if you tried to solve the equation, you would not find anything. If you try to solve those symmetric equations or the parametric equations, you would never find anything. The last thing I wanted to talk about was some surfaces. Let's reset X, Y, Z, and let's talk about some surfaces. So, the first thing we talked about was some cylinders. Like, for instance, Z x squared plus y squared equals 1. So there's your cylinder. It's hollow. See, nothing inside. And it's a perfect circle that gets lifted. See, if I look right down from above, it's going to look like a circle. We just can't quite see it if we look exactly from above. And like we pointed out in the video, if I change this to a Z, what should happen? Boom. Now the Y is missing and we're directed along the Y like a tunnel. Okay? Bam. I guess it's a tunnel either way. We could also do a parabolic cylinder. There I go, messing up. What makes this a cylinder? 4 minus x squared. There's only two variables present. And there's our upside down half pipe. Okay, it's a nice sheet. Surface, right? Hollow objects. And if I change that to a y squared, z equals y squared, there's what I was calling a half pipe over and over and over again. A perfect little parabola just projected along one direction. So cylinders aren't that interesting. let's do ones that I was too scared to make, like x times z equals 1. Uh-oh. Z equals 1 over x. Even Geogebra freaks out about this, but it's a hyperbola just projected along the y-axis. And now you see why I was too scared to draw it. I don't think it would have gone very well. All right. End of self-effacing comments. So after we finished doing all those cylinders, we started talking about more complicated objects. What do I mean by more complicated objects? I mean more complicated surfaces. Like, for instance, our ellipsoid. If I have 9x squared plus 4y squared, already graphing a paraboloid because it thinks that z equals this. We'll talk about that in chapter 14. Plus z squared equals 36. There's our egg shape. There's what I was trying to draw. It's hollow, and Geogebra is trying to do a good job of rendering that. And it's you should see how it's an ellipsis that way, an ellipsis this way, and a different ellipsis this way. They look very similar because it's much more stretched in the z direction than the x or the y. There we go. Let's go back to the x and y. And then we basically just started manipulating this. So if I go from all 3 positive to 2 positive and 1 negative, what should this do? 2 positive, 1 negative is a hyperboloid of 1 sheet. Ooh, ah. So there's the oval we have. You see that cutoff in the xy plane. And there's another trace in the bottom. Cool. Now what would happen if I turned it? So there was 2 negatives. Well, that's going to be a hyperboloid of 2 sheets. Whoa, it's all crazy. But you see how it ends up projecting out? I'm just realizing that 1 sheet hyperboloid, like a vase or a vase, however you want to think about it, a vase. I don't know. I don't know how you people say things. All right. Plus, maybe it would look nicer if I make the x the negative because it's bigger. Sure, somewhat nicer. And then there's one down here. You just can't see it. Okay, there we go. Cups. I don't know. What's left? So 1 sheet, we did 2 sheet. We did cones. Let's go to cones. So cones is where we start losing one of the squares, and we start losing the constants. So I'm going to put 0 over there, and make it z. There's our cone. And in case you couldn't tell me what was happening before, if I change it so that x was positive and the other 2 were negative, it'll be directed along the x-axis. But you see, because the x is so big, it looks ugly. It just gets dramatic. Okay, so the odd one out is going to be the way we directed it. So let's make the y the odd one out, huh? Let's make it y positive, the other 2 negative. Okay. Cones. Rays of light, however you want to think about it. Focal diagrams. Cool. Then we started doing the ones where they are actual cough functions, where we don't have all 3 squared. So something like z equals 4x squared plus y squared. This is our elliptic paraboloid, or just paraboloid constant. Classic. Maybe I'll make it a bigger coefficient of y, spread it out a little more. Sorry, a smaller coefficient of y. That's what I meant. My mind's all over the place. Oh my gosh. No. Whew. All right, so the smaller that coefficient gets, the bigger it's going to get stretched out in the y direction. And if they have the same coefficient, it's a circular paraboloid, okay? Just a nice Big old paraboloid. What gets weird is when one of them becomes negative. And that's the Pringle type shape we were talking about. This is an elliptic paraboloid. It's hard to see how it's a paraboloid until you start looking at it like that. Oh, I see a parabola. Or like that. I see a parabola. I'm not talking about down here, the empty space. Although that's helpful. It's a trace. Up here, it's a parabola too. Okay? That's what I'm saying. All right? So this Pringle-looking guy is what we're talking about when we talk about elliptic paraboloids. I encourage you to play around with Geogebra. Please, please, please play around with Geogebra. Get your feet wet. Get acclimated to the new 3D space you live in. I mean, you've lived in it your whole life, but, you know, the mathematical description of it. We want to be able to describe surfaces so we can do calculus on them. Thanks for watching. See you in the next video. Bye.